Be more specific, please.
Is it just an open?
Oh yeah. I've planned nothing. I expected you all would tell me what is most important to talk about. Go for it.
Would you mind going over that one that you were talking about kind of in the webwork with like the completing the square?
Yeah. Do you remember exactly what the question was?
Maybe.
Okay. I could probably come up with one, but
what? I mean, that's like I can find it. But in the meantime, if you wouldn't mind doing like sort of the like trig ones, the trig.
okay. So here's the completing the square thing will work with this. If you don't mind doing that. Okay. So yeah, I don't think this is exactly like anything that I assigned you, but should help. So I want to complete the square on this. So how is that done? So basically what I want to do here is what I want to get toward is this form here. Basically, I know I'm subtracting the variable squared. So basically what I'm looking for is I'm going to have something of this form, a squared minus u squared du. But now we have to kind of do the completing the square is going to help us figure out what our a's and u's are. So first thing I want to do is separate my constants from my variables in here. So I want to complete the square. So basically I'm trying to figure out what number, like what constant can I add to this to make that happen? Actually, I'm gonna do one thing to make this simpler to look at. I'm gonna factor out the negative sign as well. So minus something plus 2x plus x squared. So how do I find out what constant I can put with the x squared and the 2x to make that a perfect square?
1/2 b squared.
Right, so basically that comes from whatever this coefficient is 2, I'm going to cut that in half. So divided by 2 equals 1. And then 1 squared equals 1. So that's what goes there. So this might seem kind of arbitrary, but why did we do that? Can I factor x squared plus 2x plus 1? What does that factor to? So it factors into x plus 1 times x plus 1, right? And so that's the exact reason why we complete the square. Now this binomial here is going to be a perfect square. So before we write that, basically I introduced this 1 here. So I have to do something to counteract that, right? Otherwise, I've fundamentally changed the formula or the function that I gave you. So what do I have to do to counteract, to balance that 1 that I've introduced? Actually, I'm going to add 1. Why am I adding instead of subtracting? Right, so basically I have anything that I put inside this right-hand set of parentheses is being subtracted. So to counteract, I add.
So is it always going to be added?
It's always going to be counteracting whatever this is.
So if that was a plus sign, it would be subtracted?
Yeah, and to go a little further, I think there was at least one in the web work where like outside parentheses there was like a 4, like there was a 4 multiplied by the whole parentheses. If that's the case, then you have to subtract 4 times whatever the amount is. So basically, bottom line is whatever constant you introduce, however it affects the overall function, that's what you have to balance. So I'm not really adding 1 to this thing, I'm subtracting it, so I have to add on the outside of this parentheses. So kind of a subtle, it's an important idea, but it's subtle and a little tricky. Anything else to talk about with that? Okay, if we're good where all these pieces came from, we can clean some things up. So now this becomes the square root of 7 minus what? How do we say this factored?
X plus 1 squared.
X plus 1 squared dx. I believe there's a formula for this. I don't remember what it is, but I think it is number 30 on the tables I gave you. It's one of the one. Remember, 30 is one that shows up a lot. But basically, let me ask this: now that we have it like this, do you feel good using the tables with that? One thing I do want to point out is this. I'm pretty sure the table I'm looking for, the left-hand side of it looks like this: the square root of a squared minus u squared du. If anyone's looking at the tables, can you confirm? Since I think that's the case, let's figure out what a and u are for us. What's our a? Radical 7. What's our u? X plus 1, which means du is what? dx. In that case, then I think sometimes you have to worry about the du that you have being like a multiple of the one that's actually in the table. In this case, you probably don't. You should just be able to use the table directly. Do we want to see that, or okay?
Can you do it? See what this-
I can if someone tells me what it looks like. I don't remember what that rule looks like. Okay, so if
I did it on Webwork and it gave me a different answer than the one, it listed like on the fence.
oh, okay, I'm sorry I didn't see that.
Maybe. A little bit different. It's like this for. A squared plus B plus C.
If it was ax squared plus bx
Or
plus
number
number 3,
Number 30.
I think it is 30. What's the right hand side of 30 look like?
It is. The equal or it's 1/2 x for x squared plus or minus a squared.
1/2 x square root of
X squared plus or minus a squared. And then plus or minus 1/2 a squared. And parentheses x plus x squared plus
x plus square root of x squared plus a squared. Okay. So I think because of that, so the left hand side of the equal sign, is it just the square root of a squared minus x squared?
Oh, wait. It's that one that you wrote down.
Mhm.
Does it matter if the orders switch? 'Cause
Yeah, it
would
does.
It would be 31.
31.
It's the exact same thing as before, except instead of ln, it's the inverse of tan.
Okay.
And then all of the plus or minuses are.
Maybe I should look at it.
Yeah.
Just want to make sure.
It's the same thing, sorry. It's
No, that's okay.
it's the same one, except. These become minuses.
Okay.
Yeah.
So swap out the natural log for inverse tangent. Okay.
Yeah, and then
It's also what?
the inverse of tan is x times the square root of a squared minus x squared. Everything's number 3.
Okay, so this is. All right.
I know probably just for people to look at it. 'cause
Yeah.
it's hard to, like,
Yeah, I can't erase on these whiteboards. I don't know why. So are these the tables that I posted, or are you looking straight in the book? They should be the same.
These are like a scanned PDF from like the textbook of all the.
Okay.
It might be a different.
Well, in the one you gave us for 30, it's the same, except after the 1/2, the second 1/2 is squared, it's arc sine of u per a.
Okay. For consistency's sake, can you give me the 30 of the thing I posted?
Yeah, it's just instead of tangent of whatever that is, it's just arc sine of
Okay,
and then everything else.
you know what, let's try to declutter some of this stuff. I've redacted so much stuff, I don't even want to post this with all the
So it's u over two
U over 2.
squared minus u squared.
Yeah.
Plus u squared over 2. Arc sine over a.
Arc sine of what?
U over a plus c.
Okay,
Inverse arc sine.
good point. There are 2 ways to write inverse sine, and I combine them to make something meaningless. All right, so now we can swap in all of our things, right? What's our u? X plus 1 over 2 times the square root of 7 minus x plus 1 squared plus a squared over 2, so 7 over 2 times the arc sine of x plus 1 over radical 7 plus c. Any questions there? So I think completing the square is useful. I mean, I think you need that to get to table 30. But no matter what table you end up having to use, either for homework or for the test, make sure you really understand what your A's and U's are. If you start just like trying to like plug things in, you can run into issues, especially if there's like if you end up having to divide everything by 5 or something, if you have some multiple you need to worry about, yeah, make sure you have all those things squared away. Anything else about this one? All right, what next? Go ahead.
There's one of the facts thing.
Okay.
I like got correct with the version of it, so I was able to go over it.
Yeah, which one's that?
It was number 12, but like it's just the integral of 1 over x squared root x squared plus 25.
Root x squared plus 25?
Yeah.
Okay, this
They-
looks
they
like,
have- they have like gammas or something else. To the x question, x 25.
okay, that's strange. All right, so this also looks like an integration by tables.
It was trig substitution.
Okay, never mind, that'll work. Okay, so trig substitution. If we want to set up a trig substitution, what's a good x for us? 5 tangent, not x. Yeah. Why? Where'd that come from?
So anytime you see a plus like the under the radical,
Mhm.
it can be anything else.
Okay, so yes, basically what's under the radical, what does it look like? If it's in the form of u squared plus a squared, that leads you to believe that u is going to be equal to tangent theta. So, yeah, okay, that explains the tangent. Why the 5?
Square root of 25 is fine.
Square root of 25. So you really remember one of our kind of like primary goals here is we would love to get this binomial under the radical to be a single term, and then it's easier to deal with. If x is 5 tangent theta, what is dx? 5 secant squared theta d theta. All right, now what can we do?
You substitute all the x's.
So let's transform this. So 1 over what? 25 tangent squared theta times the square root of 25 secant squared theta plus 25. All right.
Should it be 10 squared theta under the radical?
Yeah, I'm getting ahead of myself right now. Thank you. All right, so we're done transforming the integral.
Factor out your 25.
I think there's something else we have to do.
So you have to put the details.
Right, so the reason I'm setting that trap for you, I think that's based on a lot of the questions I've seen both this semester and past semesters. That's something that often gets lost when you're doing trig substitution. Is you do all your diligence with all the things that are written in the variable x, but remember the dx has to be dealt with as well. So I do want that. I do need that 5 secant squared theta, d theta there as well. Now I would like to factor a 25 out from what's under the radical. So 1 over 25 tangent squared theta, times the square root of 25 times tangent squared theta plus 1. While we're at it, let's compact this a little bit. All right, so anything special about this step?
You can convert the tangent squared theta to secant squared theta.
Yeah, tangent squared theta plus 1 is secant squared theta, right? So 5 secant squared theta over 25 tangent squared theta. For now, I'll just leave the square root times the square root of 25 secant squared theta d theta, and hopefully now a lot of things will cancel.
The plus one goes away when it becomes just like.
Yeah, because so what does that come from? So what's the primary Pythagorean identity? Cosine squared of theta plus sine squared theta equals 1. If I divide both sides by cosine squared, I get 1 plus tangent squared theta equals secant squared theta. So that's why, yeah, the plus 1 basically gets absorbed into that. What else? Okay, so now let's deal with the radical. So 5 secant squared theta over 25 tangent squared theta times 5 secant theta d theta. All right. What now? 5's reduce. This cancels this. I'm going to pull the 1/25th out. So now I get secant theta over tangent squared theta d theta. So any questions on how we got there? Do we believe that's correct? Where can I go from there? U substitution? What's a good U?
Tangent.
Okay, if I do U equals tangent, then what's du?
Secant squared.
Secant squared is the square that's causing me to be skeptical about that. So I don't think U substitution, now U substitution might work. I don't think that substitution is going to work. Anything else we can try? What is, so if U is secant, then what is du? Secant tangent, so I still think we need another secant. Something I will advise here is, I think this is, it looks a lot simpler than it was, but I think we can make it simpler.
Can you put it as cosine?
I think I would advise looking at this in terms of sines and cosines. So secant is 1 over cosine theta, right? What's tangent squared? Sine squared theta over cosine squared theta. How does this simplify? This cancels one of these. So now I get cosine theta over sine squared theta. Okay. So PS says we can do sine or U substitution again, or now? What's U?
Sorry.
Sine theta?
Squared.
Sine squared? I think you're right the first time. Because the derivative of sine squared theta is 2 sine theta cosine theta. What's the derivative of sine? Or what's du here? It should just be cosine theta d theta. If we're just taking u as sine theta, so that u substitution, what does that allow our integral to be written as? So 1/25 times the integral of du over u squared. Is that an integral I can do? Okay. What is the integral of du over u squared? Right, so 1/25 times -1 over u plus c. What's our u again? Oh, sine. So -1/25 sine theta plus c. So Clement, is this the answer that it has?
So then they do the theta equals
Oh,
arctan of x over 5.
okay.
Well, that's what I did. But their answer choices, like I think the correct answer I noted down was the square root of 25 plus x squared over 25x plus c.
Okay, yeah, I'm not gonna worry too much about that.
But it was multiple choice, so I was like, I don't know.
Okay,
They set up the way to solve that one is they set up a triangle.
Yeah.
Based on theta, and then plug in what sine of theta would be based on that.
so I wonder how old that problem is. I mean, because I think we used to emphasize certain things more than, because we basically have to make trade-offs, and I don't think that idea that led them to that answer is not something we spent any time on, I don't think. So I'm happy with that. But yeah, you can set up a triangle so that you can re-express this without any trig functions.
That's maybe you shouldn't have to know for the exam.
So I have seen the test, and I will say we can move on. So I mean, we didn't spend any, we didn't spend any time on that in here. What else?
Could you do the integral of sine to the fourth of 4x?
Integral of sine to the 4th of 4x. We might not finish this, but we can talk about basically how it starts and where to continue it from there.
Yeah.
Okay, so how should we start?
Sine squared 4x twice.
Sine squared of 4x times sine squared of 4x.
Do a double angle on both.
Yeah, so let's remind ourselves what the double angle identity looks like. Cosine of 2 theta equals 1 minus 2 sine squared theta. That's one of the 3 ways it looks. And to be clear, I will give you this and the other versions of the cosine, the double angle cosine identity. So now that we have that, can I use that to rewrite, or maybe not? Let's isolate sine squared theta here. So cosine 2 theta minus 1 equals -2 sine squared theta. So sine squared theta equals 1/2 minus 1/2 cosine 2 theta. So now that we have sine squared of theta isolated, what can I say about either one of these two, basically these two terms here? The question is, what do they become?
1/2 minus 1/2 cosine of 8x.
Right, so the angle doubles. So that basically, yeah, I have 2 of these factors now. So basically, even though I'm not writing it like this, I have traded in a fourth degree, or like a trig function raised to the fourth power. I now have a trig function raised to the second power, along with some other things. So where would I go from here?
Four and out.
Right, so let's actually square this. So I get 1/4. Is it just a single cosine of x? Okay, minus, yep. Plus 1/4 cosine squared 8x, right? All right. So I have 3 terms now. 2 of them I think I could integrate now. But then what has to happen with cosine squared of 8x?
You can also do a double angle on the cosine square.
Right, so let's look at another version of this double angle identity. Cosine of 2 theta equals 2 cosine squared of theta minus 1. So then now I can use that to and isolate. So cosine squared theta equals 1/2 cosine. Am I going too fast? 1/2 cosine 2 theta plus 1/2. Someone double check me on that. I don't feel extremely confident about it.
Should it be a 1/2? Not over there, sorry, it should be 1/4 minus 1/2 cosine of theta. 1/2.
Yeah, I agree with you. Oh yeah, so 2 times a negative quarter. Okay, I agree with that. So minus 1/2 minus 1/2 plus 1/4 times cosine squared of 8x. That right there I'll replace with this 1/2 cosine of what? 16x. The angle doubles again. Plus 1/2 dx. So now how many terms am I going to have? So I'm carrying a lot of these things from the prior double angle move. Plus 1/8 cosine 16x plus 1/8 dx. So now I have how many terms? 1, 2, 3, 4 of them, and really 2 of them will combine. Can I integrate all those terms? Those can all be integrated now. So basically, you asked about sine to the 4th. Basically, it's the same techniques that reduce that power to 1. You just have to do it. That identity only allows you to reduce the power by 1/2. So it has to be done twice. What else?
If that was like.
So these double angle identities only allow you to reduce in that very specific way. So if you had an odd power, well, let's think about it, because there's more to it than that. Let's say this was sine cubed of 4x, and I want to integrate that. What would I do there?
You take out all the sides and then do the double angle for the.
So let's take one out. So the sine squared of x, or sine squared of 4x times sine of 4x dx. I actually don't think I would need the double angle identity for this. I think it might work, but I think there's another way to do this. Actually, I'm not even sure the double angle identity would work all that easily. But I do see I think there's something different we could do to make this integral accessible.
Cosine squared
I would do that because, well, let's talk about why. So this is 1 minus cosine squared of 4x, right? What does that substitution allow us to do?
You know, make DX.
Oh, sorry, what substitution, what should we have for our u for our substitution? Cosine of 4x, which means du is what? Very close. Negative 4 sine 4x dx. So if that's our u and that's our du, then basically we're gonna be able to transform the entire integral using that. So if it is an odd power, yeah, remember you can do those. There are other things you can do with those Pythagorean identities. So basically you can trade basically any even power, so basically any squared trig function for another using those Pythagorean identities, which allows us to set up a good substitution here. All right, so we've done some trig stuff, some table stuff. What else? That's a substitution, I guess.
Wraparound method, something we should practice?
Yeah, I would know how to do it.
Okay.
So it's a very, very limited thing, but I think the example we did was this. The integral of e to the x sine of x dx. Very broadly, the way this works is, actually, you tell me, how does that wraparound thing work?
Integration by parts.
So that for me is the most important thing. It's an integration by parts. So I'm slightly concerned. I would be slightly concerned about the wraparound method, but be very, very clear that be very, very comfortable with the integration by parts. So not just like carrying it out, but defining all the pieces here. So like, if I have an integral like this, and I want to set up integration by parts, what does that mean I have to do? So I need to figure out what my u and dv are. And what would you use here?
I would do U as sine.
Why?
Because U to X is easier to
Okay. So if those are my u and dv, then so what? What next? Du is cosine of x dx. So yes, we need a du that comes from that derivative. What else do we need? U to the x dx. And here's the thing: for this particular example, I don't think it really is going to make a huge difference on what what u and dv are. But I think, you know, the reason EV gave is probably true for most of you. Integration is less comfortable than differentiation is. So give yourself an easier integral if you have that choice. Go ahead.
Why does we have dx?
It doesn't. All right. Thank you. What else?
Oh, sorry. I just have a question. Okay, would there be any situation in which you would do like the DV and U separately, or would you always do the U and the DV at the same time?
I don't think I followed. So sorry, ask me again.
So like, if you have something like this, is there any part in which you would have something maybe like more complicated than this, in which you would do U and DU, and then you would have to like do like U substitution like again?
It is possible to do, and I mean, it all depends on how you set it up, right? For example, can I go back a page? I believe like during the first week of class, if I would have given you this integral, for example, sine of 4x dx, is that an integral you can do right now? What is it? Negative cosine 4x over 4. So we did that without substitution, right? But I believe strongly there was a time when we would have set up substitution for it. So And the reason I brought that up is because there might be cases where some of you will do an integration by substitution and some of you will kind of not really draw it out, not really express it, and that's fine. So yes, there are times when you might do integration by parts and integration by substitution for the same situation. But I don't think I won't say it's necessary because it's all depending on how you want to organize it and what makes sense for you. All right, question?
I just wanted to ask,
I think, oh, actually, it's 10 multiple choice, 2 free response. I feel like it's illegal to read you the cover of the test. Can't show it to you because the first couple of questions are on the front page, but 10 multiple choice problems were each worth 6 points. 2 free response questions, each worth 20. So for a total of 100. Go ahead.
how much of the table are we getting?
You will get the tables you need.
Is that the setup of all the tests or just this one?
What's that?
Is that the setup for like all the tests?
Oh, for the multiple choice versus free response?
Yeah. Is that right?
I think last semester we had at least one test that was like 8 multiple choice, 3 free response. So it'll be nearby. It won't always be exactly. Go ahead.
And we're doing the test in this classroom.
Yes.
So
Go ahead.
What's like the most important thing you'd want us to know? Like if there's only one thing you could study, what would it be?
Let's talk about the things we've gone over. So we started off with by substitution, integration by parts, trig stuff. What came after the trig stuff? Tables? No. Partial fractions, then tables. And then all the approximate integration stuff. And then improper integration, we're gonna hold off for next time. But those 6 sections, right? That's a really hard question to answer because I will tell you that what'll be asked of you are pretty well distributed between those things, but also keep in mind what things are common. So much of the things we talked about for trig substitution is substitution. So those things kind of converge in that way. Integration by parts, or not by parts, the partial fraction, which we haven't really talked about yet. So maybe that means as a group we feel relatively comfortable with it. Maybe. But what's that?
Are we gonna do long division?
Maybe you're ready for it. So the one long division we didn't hear was like I had you divide a 6-degree thing by a quadratic. I did that because I wanted you to see like 3 iterations of it in case it was like really rusty. That took a long time. I have 50 minutes. I can't expect you to do that. But if you have to do some long division, be ready for it, but it won't be that many iterations of it. But back to the question of if I had to have you study one thing, I hope this doesn't sound as much like a cop out as it might sound like, but I think at least as important as knowing how to do all the different kinds of integration is being able to look at a situation and know which one is the right one. I think so maybe something I would focus on is I think I set up the practice quiz thing on Canvas to shuffle everything. And I think that'd be good, like maybe just go through and be like, okay, this question I would do this. As opposed to like the PDF that I posted, very clearly tells you what section it came from. It takes away that decision making for you. So even if you've already gone through many of the questions on the Canvas, like the quiz, I would at least run through it. Be like, all right, a function that looks like this, I might use integration by parts, or basically figure out what the right tool for the job is. I think it's a good way to go. Go ahead.
Will like the decomposition type show up too?
Yeah, that was what I meant by partial fractions.
Oh,
Yeah, so partial fraction decomposition. So yeah, be able to do those and focus, like remember what the different like special circumstances are. Long division is one of them. So when do you have to long divide?
The numerators greater than the.
When the numerator has greater degree or equal degree. So The denominator has to be bigger to kind of, to skip that step. Go ahead.
There's a table problem where it's like 3x squared over the square root of x to the 6 minus 16
One more time, sorry. 3x squared over.
root x to the 6 minus 16. Are we have to worry about like any problems with that?
You might, but this is actually, this might be simpler than it appears. Because, yeah, there's not a heading for like higher orders than squared, but I think I could still get away with calling that. Like, I think you could probably find the table for this underneath the u squared minus a squared category.
Yeah, no, it gave us the table right here.
I'll give you the exact table to use.
It's like u over like square root u squared minus a squared. And then it gives you
Okay. Okay, so since there are questions like that in there, basically, so it's telling you use integration by tables, right?
Yeah.
And it's giving you the exact table. That's pretty standard. So, but you still have to know how to kind of manipulate things to. So what's the table it gives you, or at least tell me what the left-hand side of the equal sign looks like for the table?
it's just the integral du over u squared minus a squared.
Okay. So what they're not telling you for that example is what u is, what a is, and how to set it up from there. So I would know how to do, make sure you can do that.
So in this situation, you just do like x cubed as your.
Let's try it. If u equals x cubed, then what's du? 3x squared, that seems convenient. What's our a? 4. Yeah, I think that sets up nicely for me to use that table. Because I have my du directly, I don't have to worry about like a multiplier. And I do have u squared minus a squared. So basically from there, it becomes a matter of you making all the substitutions on the right-hand side of the equal sign correctly. What else? We have not talked about the approximate integration stuff or the partial fraction stuff. Do we need to?
Can you go over the trapezoid?
Yeah, in a bit. You have a question? Sorry.
We should know like the trapezoid is simple, right? Like it's
Yeah.
like-
Go ahead.
It was actually a question for, it was the third one. Because I solved it and I just missed one thing. Like when you do it, the partial fractions, it was a over x plus 2 plus b.
Can you remind me what the last question of the written homework is?
Yeah, the interval of 0 to 1 for x cubed minus 4x minus 10 over x squared minus x minus 6.
Okay. And what's your question?
When I checked it using the calculator,
Mhm.
it said that when you do a partial fraction, so it's x plus 1 plus a over x plus 2 plus b over x minus 3.
So x plus 1 plus a over x minus
X-
2?
X plus 2.
X plus 2.
Plus b over x minus 3.
Okay, I agree with that.
I'm just confused where the x plus 1 comes from.
Good question. Where does that x plus 1 come from? So you do have to long divide there. And to be clear, why do you have to long divide there? So the degree of the numerator is 3, the degree of the denominator is 2. So because of that, if you do long division, you will get this quotient. And you will also get a remainder of something over x squared minus x minus 6. So basically what you're doing here is after you do the division, you get this x plus 1 like as the quotient above your long division bar. And then whatever shows up in addition to that probably should just be a constant, or no. Yeah, it should just be a constant over x squared minus x plus 6. Sorry, x squared minus x minus 6. So basically, you're not doing partial fraction decomposition on this. You're doing partial fraction decomposition on whatever comes out of the long division.
So it's the remainder option.
Yeah, yeah. So I think I did this for somebody in office hours, but
The x plus 1 is just like the answer. Like-
yeah. So basically, if you were to do long division on, that's a bad number. If you're gonna do long division on 3 into 56, how'd you do that? Think back to 4th grade. 3 goes into 5 how many times? 1. 1 times 3 is 3. Subtract, you get 2. Then you bring down the next digit, right? But really, this whole thing that we do for polynomials, it's very, very similar to this. How many times does 3 go into 26? 8. So you get 18 is like your quotient, right? But what's left?
Plus the remainder.
Right. So the first way you probably did this was 18, you just write the remainder 2, right? Then when you got a little more sophisticated, you realize that, oh, it's not really the remainder. I can be a little more careful with that. It's 18 and 2 over, so, and plus my remainder over whatever my divisor was. So that's no different than when you're doing polynomial long division. You get your quotient, which is x plus 1, and then you get a remainder. But that remainder really is the numerator, and the denominator is your original divisor. So a lot of those techniques are identical, even though the things you're dividing are much more complicated. How we do?
So really from that, you can just go through the entire problem, not worrying about the x plus 1, and then add it on the backside.
Yeah, so that's
Really just looking
when you get to the end here, you're going to integrate x plus 1. But it doesn't, the partial fractions are not going to involve the x plus 1. You've already,
just carry it to the end of it.
yeah. What else? Go ahead.
So should we have to worry about,
Yeah. It might show up. So again, know how to do it, but I think at least as important is know when it's time to do it. So in this case, I have a cubic in the numerator and a quadratic in the denominator. That means I need to do long division. Yes, that's a good point. So one thing I'll point out is this. What I do partial fraction, or I do long division on this, x squared plus 1 over x squared plus 2x plus 2.
Yes.
Yeah. I would expect my quotient to be a constant, but yes, you would. So to do the partial fractions, we need to have the degree of the denominator be strictly bigger than the numerator. 2 minutes. Any more last minute things? Pep talks?
I love it, pep talk, yeah.
This is you're doing great. You're all here. So like, I think it's very normal to be anxious going into the first test because like you have no idea what my test looked like. The first one's like, in a way, the highest stakes. It's more high stakes than even the final. It's like it's the first one, but I see way more of you in here than I have seen in previous classes. That's a good sign. If you have questions, come see me. So between noon and 2 today, I will be in my office, which is in ECA 348. If you want to come by then and talk about things, you can. I'm not on campus tomorrow, but if you want to try to set up a Zoom call, I can probably make that work. My office hours are unfortunately after the test on Wednesday, but if you have questions, post them to the ed discussion. I will be all over that thing today to kind of, or today and tomorrow to kind of help you with your like last minute things. But yeah, I think you asked me the question, what would I really focus on if I could focus on one thing? Basically is, I would say that most of you know how to do all these things individually. Really focus on why would I do them in any given case.
How quick should we expect this to be graded and stuff?
I would like to do it day of. I never promise such things, but I feel the anxiety coming from you. I know you want to know, and I appreciate that. The test is over at 11 o'clock on Wednesday. I have office hours at 1:30 on Wednesday, and really I don't have anything going on between those two things. So I'm gonna try hard to get those done. Right?
Probably like in service or something, but do you offer any sort of like extra credit?
Extra credit, no, but there are ways to like Your grades are not final. I'll say a lot more about that after the test, but know that extra credit is kind of the thing the department frowns on, but we have other ways to kind of to help you out. I'll talk a lot more about that.
Actually, is there a resurrection?
There is that. So if that's something that if that's a term you're familiar with, there is that.
Okay.
Basically, if your final exam grade is higher than any one of your 3 in-class tests, it will bring the lowest one up. Only if it helps you.
For like the long answer questions.
Yeah.
I do like session prep,
Absolutely.
okay, just know when it is.
All right, what else? All right, please keep in touch. Post things on the discussion board. Otherwise, I'll see you Wednesday.
Yeah.